Section 3.3, Orthogonality. Two non-zero vectors u and v in Rn are said to be orthogonal, or perpendicular, if their dot product is zero. We will also agree that the zero vector in Rn is orthogonal to every vector in Rn. As an example, let's show that these two vectors u and v are orthogonal vectors in R4. So we'll just take their dot product. If their dot product is zero, which, spoiler alert, it will be, then the vectors will be orthogonal. So we take the first component, -2, multiply that by 1, add that to 3 times 2, add that to 1 times 0, and add that to 4 times -1, and we do in fact get 0, so the vectors are orthogonal. If S equals ijk is the set of standard unit vectors in R3, we can also show that each ordered pair of vectors in S is orthogonal. So what we'll do is we'll take, how about first I and j? So we'll take their dot product. Oops. And that's 1, 0, 0, dotted with 0, 1, 0. And notice 1 times 0 will be 0, 0 times 1 is 0, 0 times 0 is 0, so yeah, that's 0. Similarly, I dot k is 1, 0, 0, dot 0, 0, 1, which is 0, and j dot k is 0, 1, 0, dotted with 0, 0, 1, so that's 0. Remember, I dot j being 0 is the same as I dot k being 0 by above, is the same as j dot k being 0, is the same thing as saying that j dot I is k dot I is k dot j equaling 0, because the dot product is commutative. Doesn't matter the order we multiply components in. If n is a non-zero vector called a normal that is orthogonal to a line or plane, then a times x minus x0 plus b times y minus y0 equals 0, and the same equation with an extra c times z minus z0, z0, equaling 0, are called the point normal equations of the line through the point P0 that has normal n equals AB, and the plane through the point P0 that has normal n equal ABC. As an example, how about we write equations that represent the line through the point 3 minus 7 with normal n equals 6, 1, and the plane through the point 3, 0, 7 with normal n equals 4, 2, minus 5. So we'll take 6 times x minus 3, we'll add that to y plus 7, and we'll set that equal to 0. Because we were given 3 and minus 7, we subtract, we get those, and we have our normal equation 6, 1 gives us the coefficients, invisible 1 over there. Do the same thing for our plane, and we get 4 times x minus 3 plus 2y minus 0 minus 5 times z minus 7 is equal to 0 is the equation for our plane. If a and b are constants that are not both 0, then an equation of the form ax plus by plus c equals 0 represents a line in R2 with normal n equals ab. If a, b, and c are constants that are not all 0, then an equation of the form ax plus by plus cz plus d equals 0 represents a plane in R3 with normal n equals abc. Notice the c over here is a little bit different than the c over here. Basically, we get these equations by distributing, and then we just combine like terms. So notice you're going to get some a times minus x naught, a b times minus y naught, and that'll give you your constant term. That's what will become this c over here. And since we already have a c over here, we just need another letter, so when we multiply through by all the constants over here to distribute everything out, we'll end up with some constant d for our plane equation. So it's basically the same equations, just written differently. As an example, the equation ax plus by equals 0 represents a line through the origin in R2. Let's show that the vector n1 equals ab, formed from the coefficients of the equation, is orthogonal to the line, that is, orthogonal to every vector along the line. Okay, so we've got ab is our normal equation. We'll take the dot product with a point xy, and notice, well, that's just ax plus by. So that equals 0 by our assumption, which is the same thing as saying that our normal vector n1 dotted with a point xy is equal to 0. Our point xy is totally arbitrary, so that implies that n1 is orthogonal to every vector xy on the line. Let's do b now. The equation ax plus by plus cz equals 0 represents a plane through the origin R3. Let's show the vector n2 equals abc, formed from the coefficients of the equation, is orthogonal to the plane, that is, orthogonal to every vector that lies in the plane. Well, same thing. We'll just take a, b, and c. We'll dot that with a point x, y, z. And again, that's just this. So it equals 0. So that means that n2 dotted with the point x, y, z is equal to 0, which implies that n2 is orthogonal to every vector x, y, z in the plane. Next up, we have our projection theorem. If u and a are vectors in Rn, and a is not equal to the 0 vector, then u can be expressed in exactly one way, in the form u equals w1 plus w2, where w1 is a scalar multiple of a, and w2 is orthogonal to a. The idea is that we can break up any vector u into a part that's a multiple of itself, and a part that's a multiple of the other vector a, and a part that's orthogonal to the vector a. So we can basically break up any vector into two orthogonal vectors, but there's only one way to do it. So since the vector w1 is to be a scalar multiple of a, it must have the form w1 equals k times a for some constant k. So our goal is to find a value of the scalar k and another vector w2 that is orthogonal to a, so that when we write w1 plus w2, it actually equals u. We can determine k by writing u equals w1 plus w2 equals ka plus w2. We'll just replace w1 with ka. So therefore, u dotted with a is equal to ka plus w2 dotted with a, which is k times the length of a squared plus w2 dotted with a, because we can just distribute along the dot product. And when we do ka dot a, we get a dot a is length of a squared. Since w2 is to be orthogonal to a, w2 dot a must be 0. So therefore, k has to satisfy the equation u dot a equals ka squared, because this quantity has to be 0. Okay, so from there, we can divide both sides by the length of a squared, and we'll get that k is equal to u dot a over the length of a squared as the only possible value for k. So then we can write w2 equals u minus w1, which is, again, u minus ka, which is equal to u minus this thing replaced into k times a. So from there, we see that w2 dotted with a is equal to this thing for w2 dotted with a. And then if we do our distribution, we get, a dotted a is going to be length of a squared, which will cancel with the length of a squared. And then u dot a is just u dot a. So we'll get u dot a minus u dot a which is 0. So that's perfect. This is exactly what we wanted. The vectors w1 and w2 in the projection theorem have associated names. The vector w1 is called the orthogonal projection of u on A, or sometimes the vector component of u along A, and the vector w2 is called the vector component of u orthogonal to A. The vector w1 is commonly denoted by the projection of u on A, and it's just exactly as it was in our theorem. See? In which case it follows that w2 is u minus this guy, so it's u minus the projection. Let's do an example real quick. How about we let u equal 2 minus 1, 3, and a equal 4 minus 1, 2. Let's find the vector component of u along A and the vector component of u orthogonal to A. So first, how about we get the dot product of u and A? So u dotted with A is 2 times 4 plus -1 times -1 plus 3 times 2, which is 15. The length of A squared is equal to 4 squared plus -1 squared plus 2 squared, which is 21. So now we can compute the projection of u along A, and that's just the dot product u dot A over length of A squared times A. So that's 15 over 21 times 4 minus 1, 2, which is equal to 20 over 7 minus 5/7, 10/7. I can also get u minus this quantity. Well, I don't know if quantity is the right word. U minus this vector. And I'll get 2 minus 1, 3, minus 20/7, minus 5/7, 10/7, and that equals minus 6/7, minus 2/7, 11/7. Next, let's find the orthogonal projections of the vectors e1 equals 1, 0 and e2 equals 0, 1 on the line L that makes an angle theta with the positive axis, x-axis. So how about we draw what this looks like? So here's x, here's y, and how about I make this my line L? I'll make e1 this vector, so that's just 1, 0, and I'll make e2 this vector, so that's just 0, 1. Then I'll just make A some vector that goes along L. Remember, this angle over here is theta. I would like to figure out what the coordinates over here of A are, but if I go down over here, notice I have a triangle, that's theta, so this is just going to be the cosine of theta. And if I go along over here, this height would just be the sine of theta. So A is coordinates cosine theta, sine theta. Since A equals cosine theta, sine theta, we have that the length of A is equal to the square root of sine squared theta plus cosine squared theta, which is just 1. So that means that now we could take E1 dotted with A and get that that's 1, 0, dotted with cosine theta, sine theta, and just get cosine theta. And we can divide the length of A that we just got, so we can get that the projection along A of E1 is equal to E1 dot A over the length of A squared times A. So that's just cosine theta from over here divided by 1 is just still cosine theta. We'll multiply that by A, which is cosine theta sine theta. So that means that we'll get cosine squared theta sine theta cosine theta. We can also get E2 dot A, and that'll be 0, 1 dotted with cosine theta sine theta. So that's just sine theta. That means that the projection of E2 along A will just be E2 dotted with A over length of A squared times A. And we calculated that E2 dotted with A was sine theta. Length is still 1, divided by 1 is just sine theta, times cosine theta sine theta for A. And that's just sine theta cosine theta times sine theta squared. Let's now use the result in part A to find the standard matrix for the operator T that goes from R2 to R2 that maps each point orthogonally onto L. So the matrix A will be built out of T of our standard basis vectors. So it's T of E1, T of E2. And if we take T of E1, we already saw that that's cosine squared sine cosine. So we get cosine squared sine cosine. That's our first column. Our second column is T of E2. So that's sine theta cosine theta sine squared. So sine theta cosine theta sine squared. And that equals cosine squared. But sine theta cosine theta, we can remember 2 sine theta cosine theta is sine of 2 theta. So 1 sine theta cosine theta is half sine 2 theta. And get half sine 2 theta over here, and then just sine squared. This orthogonal projection matrix is actually pretty important, so we'll name it P theta, or denote it by P theta. I'll just rewrite it so that we'll keep it as a formula for later. Cosine squared sine theta cosine theta sine theta cosine theta sine squared, and that's equal to cosine squared half sine 2 theta half sine 2 theta sine squared. See, I told you it was important. We're going to use it right now. How about we use part B of example 5 to find the orthogonal projection of the vector x equals 1, 5 onto the line through the origin that makes an angle of pi over 6, 30 degrees, with the positive x-axis. So that's P of pi over 6. We'll get cosine squared pi over 6 sine pi over 6 cosine pi over 6 sine pi over 6 cosine pi over 6, Notice just because we can write it as half sine 2 theta, we don't always do that. So this is just easier to compute both. And sine squared pi over 6. Because this way we're already computing, sine and cosine pi over 6. Or, yeah, because we have sine squared and cosine squared. So the other form was more compact, but sometimes this is easier to compute. You get 3/4, square root of 3/4, square root of 3/4, 1/4. Okay, so now let's apply that to this x they gave us. So we'll take pi over 6, multiply it by x. So that's 3/4, square root 3/4, square root 3/4, 1/4, times 1/5. And that equals 3 plus 5 root 3 over 4, root 3 plus 5 over 4, which is roughly 2.91, 1.68 if you use a calculator. So that's the same thing as saying that p of pi over 6, 1/5 is roughly 2.91, 1.68. The reflection about a line L through the origin that makes an angle theta with the positive x-axis is given by h of theta equals cosine 2 theta, sine 2 theta, sine 2 theta minus cosine 2 theta. We could just verify this real quick by drawing this out. So here's x, here's y, and then I'll make this x, and I'll make this L, and I'll make this h theta of x. Notice this vector over here is just the projection of x, so that's p theta of x. So that means that this little piece right over here, this vector, is p theta of x minus x, geometrically. This whole vector is h theta of x minus x. So if I multiply that by 1/2, I should get as much as the red one. So these guys would be equal then. So solving for h of theta, we can see that h of theta h of theta of x, that should be equal to 2 p theta minus the identity times x. So h theta is 2 p theta minus the identity, and you could verify that that's actually what we get over here as h of theta. Anywho, how about we find the reflection of the vector x equals 1/5 about the line through the origin that makes an angle of pi over 6, again 30 degrees, with the x-axis. So this time we'll calculate h of pi over 6, and that'll equal the cosine of pi over 3 sine pi over 3 sine pi over 3 minus cosine pi over 3. And that's just 1/2 square root of 3 over 2 square root of 3 over 2 minus 1/2. Okay, let's apply that to x now. So h pi over 6 times x, that'll be 1/2 square root of 3 over 2 square root of 3 over 2 minus 1/2. times 1, 5. Okay, so that's 1 plus 5 root 3 over 2, root 3 minus 5 over 2. Using a calculator, we can approximate that as 4.83 minus 1.63. So that means that h of pi over 6 of 1, 5 is about 4.83 minus 1.63. A formula for the norm of the vector component of u along A can be derived as follows. We'll take the length of the projection u along A, so take the length, but then the length of the dot product, well, that's just the absolute value. Length of a length is just, again, absolute value. It's already going to be positive. And we just take the length of A separate. So we can get rid of the absolute value on the bottom because this is already positive. So we'll just take the absolute value of the dot product. So then that means that, oh, well, I can cancel that with that, and I'll just get that from my formula. Next up, we have the theorem of Pythagoras in Rn. If u and v are orthogonal vectors in Rn with the Euclidean inner product, then the length of u plus v squared is the length of u squared plus the length of v squared. Great, our Pythagorean theorem. Since u and v are orthogonal, we have that their dot product is 0, from which it follows that u plus v squared is u plus v dot u plus v, which we can distribute out. U dot u will be u squared. U dot v plus u dot v is 2 u dot v. It's u dot v plus v dot u, but dot product's commutative. And then v dot v is v squared. But remember, dot product is 0, so this disappears, and we just get u squared plus v squared. It should make sense that we get this, because if these guys are orthogonal, you should think of that as being perpendicular. So you can just basically draw a triangle, get Pythagorean theorem. We showed in example 1 that the vectors u and v are orthogonal. How about we verify the theorem of Pythagoras for these vectors? So we'll take u plus v, and that's minus 1, 5, 1, 3. We'll find their length. So that's just square root of each of those things squared. So that's 36. You can work it out. The length of u squared plus the length of v squared is 30 plus 6. So yeah, theorem of Pythagoras applies. U plus v squared is u squared plus v squared. The distance d between the point P0 and the line ax plus by plus c equals 0 is the absolute value of ax0 plus by0 plus c divided by the square root of a squared plus b squared. The distance in 3 dimensions between the plane and the point is this, again, absolute value over the square root of a squared plus b squared plus c squared. As an example, let's find the distance d between the point 1 minus 4 minus 3 and the plane 2x minus 3y plus 6z equals minus 1. So I'm going to move over to minus 1. So I'll get 2x minus 3y plus 6z plus 1 equals 0. That way I can have a d over here, and it'll be in the same form. So I'll get the distance d is the absolute value of 2 times 1 plus negative 3 times negative 4 plus 6 times negative 3 plus 1 divided by 2 squared plus minus 3 squared plus 6 squared, all under the square root. And that's the absolute value of minus 3 over 7, so it's 3/7. the planes x plus 2y minus 2z equals 3 and 2x plus 4y minus 4z equals 7 are parallel, since their normals 1, 2 minus 2 and 2, 4 minus 4 are parallel vectors. Let's find the distance between these planes. So we have, let's see, how about we set y and z equal to 0 so that we can get a point. Because if y and z are 0, then x is 3. So we get the point P0 as 3, 0, 0. So that'll be for this guy over here. X plus 2y minus 2z equals 3. Now that we have a point in the plane, we can use this formula for the distance. Remember, they told us that the planes are parallel, so they have the same distance at any point, so we could just find any point we want. So we chose one convenient. We just set y and z 0. Okay, so now we just find the distance between that point and the plane, and that'll be the distance between the two planes. So that's 2 times 3 plus 4 times 0 plus negative 4 times 0 minus 7 in the absolute value over 2 squared plus 4 squared plus negative 4 squared. Take the square root of that, and that's just 1/6.